for a whole minute. So shall we start?
Yep, let's get started.
So let me first, so welcome everybody to the session today, and we have a fantastic cast of speakers. I'm really looking forward to that. So just a couple of housekeeping things. If you are an attendee and you want to ask questions, raise your hand. If you are a panelist and you want to ask questions, you can unmute yourself. I think all the speakers are okay with this, and or you could post things in the chat. What else? We'll be on Gaza Town after that. So let me, without much more housekeeping, you remind me if I forgot something, introduce our first speaker today. And I'm really happy to have Sasha Razborov give the first talk today. I've heard it before and it's beautiful. So speakers today hardly need any introduction, but just to mention one of the many things, Sasha Razborov is famous for being one of the few people who proved lower bounds, original lower bounds for monotone circuits. He had done beautiful work in bounded arithmetic and proof complexity. In bounded arithmetic, last Wednesday we talked about RSUV isomorphism, for example. And he's also well known for probably the most important barrier result in circuit complexity and also in bounded arithmetic, the natural proof barrier. And hopefully you might hear a bit about it today. In addition to that, done some quantum complexity, communication complexity, some other complexity, and some deep mathematics, flag algebras stuff. He unsurprisingly got numerous prizes for that. Just to mention the Gödel Prize for the barrier results for natural proofs, and I think an Ivan Linas Prize for circuit lower bounds. There is way too much to say, but I'd rather let him speak for himself. So please, the floor is yours.
All right, thank you very much, Tonya, for the nice introduction. Again, if you want to ask questions, please unmute yourself and ask, highly preferred method. So, and first of all, this talk today will be highly speculative. And it is, I apologize that it's about somewhat old stuff. I will talk here at Simon's, virtual talk somewhere in May on more modern things. And another apology I already made is that some of you or many of you have seen this talk before, a longer version of it, but I still hope I made a few changes. All right, so we start with our favorite program, P versus NP. I think at this point in the game, everyone here knows what it is, but we are going to tweak this question a bit. So the first version we may ask, and that's how it was attacked. People try to attack it in this form. It's a slightly stronger version, and it's asking whether languages in NP have polynomial size circuits. Let me remind you that P/poly is anything is non-uniform P, which means everything you can compute where it's polynomial size circuits. So then we can further relax this question and ask, are there any explicit Boolean functions not in P/poly, with explicit being in good old sense, in mathematical sense, not necessarily NP, or something which you would recognize as explicit? And then we may ask this question, which looks ridiculous, but as we will see, it is not, at least for the purposes of my talk today. And this question is actually even more relaxed version. Are there any Boolean functions that cannot be computed by polynomial size circuits? Well, of course, I have put here a question mark, but of course we all know that it is the case. It's classical result by Shannon, somewhat clarified by Lupanov later, and it says that it is indeed the case, and we have functions, and actually almost all functions are hard. So here is some notation. C of Fn is the circuit size of my function f in some standard basis. So almost all of them are exponential. Almost all functions are exponential, and that's basically the whole proof. It's a simple application of the pigeonhole principle, but let's look closer at this proof. So what's really going on is that if you want to run this argument, then you want to be able to count really well. And by really well, I mean you are going to be able to count really large numbers. So you want to count up to double exponential size, double exponent in the number of variables, because it's the overall number of your Boolean functions, or at least up to this number, but still you have to count really a lot. And that will be the main theme in my talk today, is that actually, the main principle is what you can do depends on how well you can count. Right. So maybe you should use it in K-12 education in classes on arithmetic, but that's really, that will be the dividing line. Everything will depend on what is the maximal number you can see in your arguments, and you can count up to that number. So let me now revisit this question. Are there any Boolean functions not in P/poly? And for the purposes of my talk, first of all, we are going to be interested in proof theory. So we are going to study whether this equation is provable somewhere or not, or using some class of methods. And if there are any logicians here or proof theorists, then we will understand, for the purposes of this talk, we will understand proof theory slightly more broadly. It's not necessarily a first-order theory or propositional theory. It's something that, some class of methods that you can rigorously define. That word we don't compromise on. It must be rigorously defined, but other than that, it can be described by various means, and natural proofs that we will see is one of the examples. So, and let me now put here my favorite, one of my favorite sentences, because, well, you do algorithms, you do whatever, you prove theorems, and when you cannot do something, then you start to explain others why you are so stupid. And as you see, this principle was not invented by complexity theorists, but still, that's basically what we are going to do in this talk. As I said, it's highly speculative, so let me end. Yes, I forgot to say that it will be one of our guiding principles, is that we will be interested in proof systems, again, broadly understood, for which even that statement is supposed to be hard. So only in those proof systems in which you can first formulate this statement, and second, this blue word any does not make your life any simpler. Proving that NP is not in P/poly is supposed to be more or at least as hard as proving it for any Boolean functions. Let me briefly state a few motivations. Right. So first of all, because mathematicians do it, we know great independence result in mathematical logic, axiom of choice, continuum hypothesis, Gödel's incompleteness theorem, and it's self-explaining that it is interesting. The second motivation, it actually started in the book by Gary Johnson, 79, of 79. In the, as many of you know, in the first chapters, they carefully laid down this principle that the theory of NP completeness is good for many reasons, but one of them is that you can explain to your boss why you cannot do the job. So that's the second reason. The third reason, it is of course because since these problems so far, mathematics never gave up on its problems. It kept solving them, if necessary, for centuries, and as we know, eventually they get solved. So we have to continue, and like in complexity theory, computational complexity theory, I mean, it is the same whole. We are going to focus our research in the right direction by just saying what and why does not work. So it's the ideology that we used in our paper on natural proofs. Of course, as Stephen and me had expected, everyone misused that sentence and took the paper like don't do circuit lower bounds, do something else. Well, we cannot do anything about it. It was not our intention. Our intention was just that we showed what does not work, and let's take it from there. And the third, but also fourth, I'm sorry, but also very important motivation is, of course, about byproducts. So again, that's what complexity theory is about. You prove something totally useless, and then something comes out of it that makes a difference in the real world, even if you did not even think about it. Or the same sort of happens in this business as well. All right, so what's next? So diagonalization, it probably was the first barrier. Let me go over this slide very quickly. So it's a proof system in my sense, right? So if you have a complexity result, then the proof system, it simply says that it should be true in all Oracle worlds. It's well defined. It's not, of course, like the usual proof system, but still it is rigorously defined. And we all know this classical theorem by Baker, Gill, and Salovey is that this proof system is not capable of proving either P is equal to NP or its complement. That's probably the first manifestation. That was probably the first manifestation of this idea that a proof system is not necessarily rules and axioms in first-order logic. It might be something else, but something reasonable. So what does it mean to be reasonable? Again, let me try. So 4 will be a magic number for some reasons throughout my talk. Let me formulate 4 constraints and wish lists that I would like to have in a framework that barrier or proof system, whatever you like, to study this kind of things. I mean. So the first, of course, is that your proof system should not be able to solve this question in the obvious way by counting. And it rules out strong proof systems like those. Well, Shai probably will disagree with this, but we will listen to what he can say in an hour about stronger proof systems. So, but for the purpose of my talk, I really don't want Shannon arguments to be formalizable in my proof system, because it's not an interesting proof. I want it to be out. So the second, which is very important, is that if you take your favorite result in circuit complexity, and we do have a few results, as you know, and by the way, it is an excellent book, one of the best books I've ever seen. So if you take any result from this book, then you really don't want to work hard on proving it in your system. You don't want to write papers, you don't want to introduce something, some new concepts, you just take it and it should be durable in your system in a straightforward way. So, and returning to my counting theme, turns out that now all those results, well, except of course from that book, except of course for the chapter that talks about Shannon counting arguments and Lupanov's improvements, all other results, they use only counting up to polynomial in the number of instances. So little n, of course, stays everywhere for the number of variables, so it is just polynomial in the number of your instances. So all those proofs, they use counting only up to this number, which is single exponential in them. Right. So the third is self-explaining. We really want proof system that people care about. And it is probably the weakest point of natural proofs, because somehow that's what we cooked up. I will show you what we did in several slides. So, but still we have some motivations, but other than that, usually it should be natural. The proof system should be somehow of interest. I cannot quantify it. And of course, the first thing is that we really want to hope to make progress. And in logic, you make progress if usually if meta-mathematics of your proof system, so what you can extract from proofs basically, it somehow matches mathematics. So Gödel's incompleteness theorem, it is meta-mathematics, is formulas that you prove, you encode them, and then it is the same mathematics about integers your proof system is arguing about. And if it looks if it looks abstract to you, then let me point out this recent breakthrough result by Albert Atzeris and Müller. They proved something extremely concrete, improved complexity, not only extremely concrete automatizability of resolution, but what has been open for decades, and they really use this self-referring argument. So it's not, if you are interested in concrete things, then you still want to have it. Right here, Shai again probably disagrees with this. We are going to listen to it later. Right, so let me remind you what are natural proofs. And I will be very quick because this talk is about something relevant, but still something else. So these are two pieces of common wisdom. So the first one is that if you want to prove lower bounds for Boolean functions, then you should look at how it looks like, study its properties, and then move it to lower bounds. And the second piece of wisdom, it says that if you want to analyze your proofs, then you should carefully look into them, do a proof system, and blah, blah, blah. So the starting point of natural proofs is that we dismiss both of them. So namely, instead of even trying to understand what our proof looks like, so we are going to think about it, sometimes creatively. Sometimes it's not straightforward, and then we are going to conclude that the same argument can be applied not only to your function of interest, but to a great deal of other functions, which which gives rise to the set of Boolean functions Pn to which your argument can be applied in a sense. And that's the only thing we need in our model. So we only look at this set Pn, and then we formalize. So sorry, it should be Pn. So Pn and Cn on this slide are the same. So, and then we simply write the properties of this set of functions. First of all, of course, we want it to make sense. And the second two properties, they are debatable, but still that's what happens in all or almost all known proofs. And you really want to understand what you are doing. So, which means that our set Pn must be computable in polynomial time in this quantity, and it must have large density. So, once you have a good method, then you really are going to be able to apply it to sufficiently many functions. Usually, it is even better than that. Usually, it is just almost all functions, but to be on the safe side. So let us check against our 4 items from the wish list. There is no obvious counting solution. You cannot count. That's why we have here constructiveness, right? So if you count up to larger than that number, then it will not be in polynomial time. So that is what we call naturalization. So there are some technicalities where it's monotone formulas, basically because it is not so easy to define a good distribution over monotone formulas, but morally you can do it. So, as I said, this is the weak point of natural proofs. So you can prove, but here is at least one justification for it, which is also well known. That it's written here. If you prove that Fn is hard and your proof system is closed under X4, then you somehow, and you understand what you are doing, then you should be able to tell which one of these two is hard, and it gives you largeness because you have then half of all functions. And here, on the 4th item about mathematics versus meta-mathematics, it is almost here because one of our axioms, it has polynomial inside of it, and we study right short circuits, small circuits, but the catch here, of course, is it really a problem that now we have changed our measure, that it's not small n, that it is 2 to the n. Is it really a problem? Well, turns out it is the main and actually the only problem about natural proofs is that you really can prove things even in this form. So that's the main theorem of natural proofs. So modular standards cryptographic assumption, there is no natural proof against general circuits. Self-defeating arguments in its pride. Good. So as I said, there is lots of work on natural proofs, and people disagree with many of these points. Some people agree, some people both agree and disagree at the same time. And let me stop it here. So, and this is one very important byproduct. So it will be the same throughout my whole talk, that we actually are interested in our inputs. We are measuring our main size measure is this capital N. It will always be the same, which is the number of instances in my program, which means that your Boolean functions are given as truth stable. And one byproduct is that this work with similarity highlighted the importance of this problem, which these days is called minimum circuit size problem. It is here, it is obvious, it is the set of all truth stables that corresponds to simple functions. And let me just say that there has been a lot of very interesting and wonderful and important research on this problem, and somehow our paper helped to understand its importance and that it is a really good thing to study. So in complexity terms, if we forget about all our motivations, then in complexity terms, natural proofs can be easily formulated in terms of this problem as is written here. Right, so that's it with natural proofs. Let's move on. And so these are the 2 points, I repeat here, the 2 points that natural proofs dismiss. Today, in the remaining of my time today, we are going to still dismiss the first point. As I said, we are interested in proof systems that actually do not distinguish between explicit functions and any functions. But we want to replace the second point with its opposite. So we really want good proof systems in the good old sense of formal theories. And of course, as Antonina already said, there is lots of work about it. So here I really want to say just a bit. So bounded arithmetic is just piano arithmetic where you focus on bounded quantifiers, bounded by terms. So you also have sharply bounded quantifiers, and it is important that it is just a normal first-order theory. No catches, axioms, inference rules. So again, as almost all of you know, S21 is the most important theory in the whole family. There is a hierarchy, there is a family hierarchy. It closely models complexity hierarchy, but I don't have much time today, so I will talk only about S21. And the fourth item in my wish list, it is answered by this fundamental theorem by Sam Bass. It's from his book about bounded arithmetic that basically started this whole subject, is that if you prove something existential in this theorem, and A is simple predicate, then you have then it can be witnessed by polynomial time function. So we see here a polynomial time that corresponds to meta-mathematics of our proof system, and it's the same concept we are going to study. Therefore, it's good news for us. So sorry, it should be S21 reversed. So now, again, it's a shorter version of the talk. I have to skip many details that I gave before. And but you can formalize the question we are interested in. So here I put sub-exponential function to avoid certain trivialities. And this is the question, whether we can prove the existence of a Boolean function Fn. So there is no obvious counting solution because we don't know the answer to this question. We don't know whether it is provable or not. Therefore, there are no counting solutions, obvious counting solutions. This is the second part is also very easy and very natural. So if you look at the same statements, but for for restricted circuit models, then you can really do it in this system. It is extremely straightforward. So I did it once, and mostly I focused on the question, are there weaker systems than this where you can prove all that stuff from Stas's book, and so it is very natural, very simple. So of course, bounded arithmetic, that's what we love for many good reasons. It's not only because we are able to do this stuff. And now comes an interesting part. So that I will show on the next slide, and it's good that I was able to get to that slide. So, but one clarification is that we cannot hope to get to all the way up to this bounded arithmetic unconditionally. So like in natural proofs, I do allow you arbitrary reasonable complexity cryptographic assumptions that are short of NP is not equal to KNP, because that makes the whole game trivial. So again, it's a short version. Let me just mention a competing framework, which is promoted by Yankovic. So in this framework, you allow even more restricted counting. You cannot really count up to capital M, but on the other hand, it's no longer simple existential formulas. You allow lots of quantifiers. It's a very interesting framework, connected in many respects to what I'm talking about here, but I don't have time to talk about it. So, and now, again, it should be S21. So, and now we can reformulate the questions we are interested in terms of propositional proof complexity. Because, again, there is a catch here due to sharply bounded quantifiers, but morally, Sambas theorem almost implies that if you prove this in S21, then there should be some explicit sequence of functions for which you can prove the same thing. And once you have quantifier-free statements, or only with sharply bounded quantifiers, then you can translate it to propositional proof complexity, propositional logic. You can express it as a propositional formula, the fact that the function fn is hard, and the size of this formula, again, we use our convention or our main principle that we don't care how we encode it. It's simply given by its truth table. We have enough memory or enough time to just encode it as a truth table and measure everything as a polynomial in terms of the length of this truth table. And now comes the main slide. So we have this square, namely we have proofs in bounded arithmetic, and it is very popular topic, connections between bounded arithmetic and uniform complexity classes, given by various witnessing theorems. Sambas theorem was the first theorem from this family. If you have something in bounded arithmetic, a proof in bounded arithmetic as to 1, then you get something polynomially time computable. So if you have sigma, if you have delta 0 be quantifier-free formulas, then you can translate them through propositional proof systems, and this will give you will just work in much more convenient and more elegant propositional world. For example, S21, again, S21 is different. S21 gets translated to extended Frege. So this is also, this connection is very is standard in computational complexity. So every uniform complexity class, essentially every uniform complexity class, you have associated non-uniform class. So what we really need is the force arrow, right? So you would really expect a force arrow on this picture. I give you a propositional proof. It argues about computational concepts, and you want to extract something computational out of it, and then apply your knowledge like we did in natural proofs, or in this implication, apply our knowledge to get conditional results. And it's embarrassing that we almost cannot do it. And I don't understand why. Right. So let me give you a few definitions for Razborov systems. Resolution. Extended Razborov system. Well, I believe that everyone knows what it is, so I have only less than 10 minutes left. I don't want to spend time here. Right, so the success story, and it is precisely a model case of what we would like to have. Idea is called feasible interpolation. That's precisely what we would love to have. So I give you a special pathology, and it all is applied here. And then you ask, and then you extract from it something computational, which is called feasible interpolation. So you can apply it to several systems of interest, but then turns out that you cannot go very far along these lines because simply feasible interpolation fails for more for stronger systems, for systems that we are really interested in. Well, I mean, we are interested in all those systems, as well as everyone at this workshop already knows by this time, but for different reasons. So here is a byproduct of this. One byproduct of this, it is simply because it is simply one quite amazing thing about proof complexity is that really it is the same phenomenon. Unlike circuit complexity, we really don't know if there are any hard tautologies for Frege or extended Frege proof systems. There is no counting argument here. So in this paper, they tried to come up with some examples, but I guess they indicated themselves that it was not very conclusive, and most of those results were solved, I mean, short proofs in Frege or extended Frege were found later on. The principle is that these systems are really hard. So we really want some arguments that we don't understand ourselves. And at the moment, I have only two, and I think everyone has only two reasonably convincing examples of what might be hard for Frege or extended Frege. The first is random CNFs. It's just because we really don't understand why. If you pick a random CNF, why is it unsatisfiable? You have to count for that, and it's beyond the reach of our system. And it is the second example is coming from this business of proving that NP is not equal is not NP/poly. It is the second candidate hard topology. And it is, again, it is, we don't understand it to the extent that we don't even know if it is true or not, which makes it a perfect candidate. So I have only a few minutes left. So let me very briefly say that we have some ad hoc results for so that's now what we are going to study. We are going to try to understand why this thing is difficult for various propositional proof systems. We have a few unconditional results, and it also does not go quite far. So that's basically the last thing I want to show. And Tonya, do you have 5 minutes?
Sure, why not?
Right?
Please, yes.
Okay, good. So I will try to finish in 5 minutes. So that's one suggestion that is still which may lead anywhere. So improve all the stuff to stronger proof systems. So let me start with reminding you about natural proofs. And the way you prove it is that you construct pseudo-random function generator. If you have an ordinary one-way function, then you get an ordinary pseudo-random bit generator out of it, and you can either construct it using general construction by Mikali, Goldwasser, and Rakov, or you can take, for example, Nissan-Wigderson that immediately gives you a conjectural function generator, and this is basically the whole proof. You have to supply a few details. So the idea is to try to understand what it looks or what it might look like in the propositional world. So again, I have a mapping. I have a proof system P. So our idea was that if I give you Nissan-Wigderson generator or any other generator, any other reasonable generator, and I give you identically zero string, right? And I ask you, is it true or not that this string is not in the image of your generator, is not generated by any seed, then it's really impossible to do. So if your generator is reasonable, then you cannot answer this basic question. You cannot really pinpoint any particular string in the image of the generator that is not in the codomain of your generator, that is not in the image. And that's what we take as a definition of our hardness. So the idea is, of course, that we can use, so if I give you any string B, then your proof system does not prove that B is not in the image of this thing. So answer, the proposal is simply to try to somehow write pseudo-random generators is something that is well studied in computational complexity. And so the proposal is, of course, to search for this missing fourth arrow using maybe at least as inspirations what is known in the computational world. So in a sense, good news is that it extends feasible interpolation. So if you have feasible interpolation for your system, then you basically can do it with a slight twist of your generator. And this is the main conjecture, is that if you take any Nissan-Wigderson generator just for simplicity and for concreteness, and you base it on any function, then it becomes hard for extended Frege proof system. So that was made almost 20 years ago. There has been some work, but not much on it, and it is still wide open. And basically, I would like to, that was the main purpose. One of the main purposes of my talk is to draw attention to this conjecture. So here is what we know. We don't know very much. So we know this conjecture for widths, resolution widths, for polynomial calculus. For even for resolution, it is frustrating because we don't know it for exponentially many output bits, only n squared. And it is a very important work by Jan Krajicek, so which is again the same principle. You can iterate these generators as you do in circuit complexity, and for example, for resolution, you can get slightly better. You can get 2 cube. And that's probably the best you can do at the moment. It is the proof system where you can lift this stuff. So pseudo-random generator for this system, well, I hope you know what it is. It is the strongest system for which within all these statements. So, and as I mentioned several times, there are many other suggestions. So, the obvious open problem, so it should stay S21. It is just the same YRSUV isomorphism Tonya mentioned before. So it is the main conjecture. Again, it is connected to model theory somehow. So now we have had several breakthrough results in cutting planes in several last years, but as far as I know, they formally don't imply unconditional hardness of this statement. It would be a great problem, accessible problem. I mean, well, unless I missed something and there is a simple reduction, which I don't see. So proof at least its hardness for cutting planes or sum of squares. As far as I know, it is open. Unconditionally, conditionally, you can apply feasible interpolation. And the same equation for bounded depth Frege. We missed some techniques, basically, random restrictions were not suited very well for the task, but these people, they explained to us that it is much more versatile method than we had thought about it. So again, even for resolution, we have to apply other methods. We don't have pseudo-random generator for resolution that is really in the range we are interested in, and it's very loose because it's very loose creation, right?
Thank you so much. This is fantastic. This is such an inspiring talk. I'll clap for everybody. Questions, comments? Please.
I have a question.
Mm-hmm.
So you motivated the search for natural proof by you didn't want to have counting up to doubly exponential. But that can be then, you could have said that the proof should be of exponential length or the proof should be in P space. Why not take a simpler definition of natural?
No, it's So no, it is not what we want to achieve. It's I view it as a test for what we are doing is right. It's sanity check. I view it only as a sanity check. It's not like it's not my purpose. But simply if your system, be it natural proofs or anything else, if it does not pass this check, then it means that it's not what you're interested in. Okay. It's not the purpose. It's not the purpose. But it's excellent comment. Thank you.
Okay, thanks.
More questions?
I can ask a question.
Mm-hmm.
You ended with a comment about lifting versus natural proofs. So I was wondering if you think there's any connection between the two in the techniques or the approaches.
No. Let me, I think it's more, again, I had to revise, which means vandalize my large talk fitted here, right? So in the long version, it refers only to this result.
Okay.
So natural proofs, so it comes here in this business, or if you have a system with feasible interpolation, right? And you want a pseudo-random, natural pseudo-random generator, then you do very primitive lifting, extremely primitive. But still you do it. Is there anything like that for natural proofs or for other systems? It's very limited question.
Okay.
Sasha, so in this diagram that you have on the slides, so you were asking about the arrow on the bottom. Mm-hmm. So your proposal is to use these what Jan Krejcik calls tau formulas.
What formulas?
Tau formulas. These formulas saying that something is not in the image of a pseudo-random generator.
Yeah,
So
whatever.
this should be the arrow down.
It's one possibility. So and it's
But
main.
is it your conjecture or that this is the right arrow, or you suggest it as one possibility? Or
No, this conjecture is made in my annals paper. It's quite official.
Mhm.
Or are you asking in the reverse direction? So if it
No,
is,
I'm asking whether this you propose this as the solution of what the arrow should be. So I know that you propose this conjecture, but do you propose this as the only solution of this arrow, or one of the solutions?
well, this solution has extremely maybe a bit dirty, but extremely powerful, something extremely powerful behind it. It might be bad, it might be totally incorrect, but we don't have anything else.
Mm-hmm.
At least I am not aware of anything that I would recognize as a project, as a plan to get it. I had tried lots of things.
Mm-hmm.
And it's very frustrating. You have an object, right, which is essentially a sequence of circuits, polynomial size circuits. Each one of these circuits computes one, because it's a tautology, and you want to get some computational content out of it, and you fail. I don't understand why. Even in 30 years, I guess, I still don't understand why we fail. So it is simply it's like democracy. I would compare this random generators with democracy. It may be a bad system, it might be a lousy system, but it's better than anything else.
I have a quick question. So you were talking about S12 as kind of the right system, the right power to talk about complexity. But in recent years, people have been working with systems that formalize probabilistic reasoning, APC1 and friends. What do you think about that?
It is, first of all, it is definitely a very interesting line of research. And I certainly don't want to say anything negative about it, but somehow I feel that, you mean this one, yeah? Okay. Somehow I don't feel quite strongly in terms of this thing. It looks like these systems, they, in many cases, they were somehow to formalize or capture particular things. It's not the case with bounded arithmetic, right? Bounded arithmetic was not invented to prove something or analyze proofs. It was invented to capture polynomial time. It's not with piano arithmetic, not the case with piano arithmetic. It was intended to capture all finite arguments. Somehow these systems, I'm not sure that they, whatever.
Well, thank you. Thank you so much. So more questions, comments?
Can you go back to the slide where you have this generator that you talk about?
What? I'm sorry.
The Nissan Wigderson generator, the first time that you talked about it.
No, it's not back. It's forward.
Yes, yeah, this one. So can you go back one slide? The one where you have the mapping from functions. Yeah, this one. What exactly? What exactly are you saying here? So I'm just trying to understand this.
So I'm saying that if you take any reasonable generator, for example, Nissan Winderson, right?
Mhm.
And
Yeah.
I ask your equation, like I give you identically zero, or almost all strings here are not in the image of this generator.
Mhm.
Yes.
Yeah.
If I am asking whether identically zero string is in the image of this generator or not, you will not be able to answer this question, regardless of any proof complexity. Just fix it in any reasonable way. Of course, you can always manually ensure that it is not there. But if you don't play any tricks, then you will not be able to answer this question about identically zero string.
Okay. Thanks.
And we simply generalize it to all other strings.
Great. So thank you so much. This is fantastic.
Thank you, Tonya. So, and I'm now giving floor to Pavel. Let me see, how do I stop sharing?
Thank you. This is great. So Pavel, would you like to share your talk and unmute yourself?
Yes.
Yeah.
So do you want to make a short break before I start?
Do people want to break now? Do people want to break after your talk?
I think a 5-minute break might be good because we have been at this 1 hour now. So maybe 10
okay.
minutes. Yeah.
Let's take maybe 3-4 minutes break.
Yeah.
And actually people can use this to ask more questions if you like. And we'll start in 4 minutes.
Okay. I just try sharing my screen. So
yeah, please.
Yeah. So how does it look like?
It's not full screen, but it's visible.
Okay, let me do it. Screen presentation.
Oh yeah, that looks great.
This should be okay.
You can see the slides, can see your mouse. That's great.
So how do I exit this full screen? Okay. Yeah, just stretch my legs.
Alexander?
Yeah,
May I ask an intermediate break question?
absolutely.
Yes, that was very, very amazing talk to me. I'm wondering, two questions. First, do you think, what is your personal belief? Does a proof system, propositional proof system exist that is strictly stronger than extended Frege? And second, what might it look like then? I don't have it.
I think it's actually, Pavel, I think it's a question to you, right?
Well, of course, Sasha knows very well these things, but
No, not about extended Frege.
Not about. Yeah, so we already studied a long time ago, and I'm going
That's what I
to
mean.
mention also in my talk is our quantified propositional calculi or calculi. So where you have the usual sequent calculus formalization, but you use quantified propositions, and they seem to be stronger. So this is just one next step after Frege or extended Frege. But there are other things like Jan Krejcik's implicit proofs.
Mm-hmm.
So you can take basically any proof system and make the so-called implicit proof system from it. And this is a kind of jump that we cannot prove that it's strictly stronger, but potentially it could be a kind of jump like in recursion theory that produces a stronger system from one proof system. And there are other things like taking first order theory as proof systems for propositional calculus, and then you get the extremely strong proof systems. So yes, where to read about it? So in Jan's book, of course. And
Thank you.
But of course, there are different opinions. So Jan Krejcik thinks that it's quite possible that these proof systems are not stronger, that they are.
Oh, theoretically, you can believe that NP is equal to co-NP, right?
Yes.
Which immediately closes all descriptions.
So should I?
So
start?
shall we start? Yeah, if you don't mind putting up the slides.
Okay.
And meantime, so speakers today need no introduction, but let me still introduce Pavel Pudlák. And if you did anything with proof complexity or with SAT circuit, you've seen Pavel's name over and over and over again. And from lower bounds, from feasibility calculation, I think your name is on most lower bounds in proof complexity that I can think of. Cutting planes, the similar result as lower bounds for cutting planes. From the point of view of mathematics, Pavel has a great book called Mathematics of First Order Arithmetic, and a more recent book, which is a gentle introduction to logical foundation of mathematics and complexity. It's gentle, but it still talks about a lot of really advanced concepts that Sasha mentioned. Also, if you do algorithm for SAT, probably the most well-known algorithm for SAT, exponential algorithm, is PPAZ. And again, this is Pavel's work. So many things that I can't even mention all of them: circuit complexity, other connections. So I'd rather let Pavel talk about this and the beautiful connection between different areas of complexity and SAT. Please.
Thank you, Antonina, for a very flattering introduction. So my talk will be hopefully short and definitely very elementary. I will not talk about new stuff. I will actually talk about things that I have already spoken a couple of times, but each time I still find some details that I can present in a better way or complement things in it. So I'll start with some background from the foundations of mathematics. We use various theories to formalize arithmetic or set theory. These theories are of increasing strength. Here on the slide, we have T2, which is bounded arithmetic. So I should have also included S12 that was mentioned before, which is a fragment of T2. Then we have a fragment of Peano arithmetic called I sigma 1, which is induction for sigma 1 formulas. A stronger theory than that is than Peano arithmetic is the so-called second order arithmetic, which is not arithmetic formalized in the second order proof calculus, because there is no any, but it's an extension of Peano arithmetic by sets, subsets of interpreted as subsets of integers, non-negative integers. Then Zermelo-Fraenkel theory, and we can go on by adding new axioms such as strongly inaccessible cardinal or the existence of measurable cardinals, and obtain stronger and stronger theories. And these theories are stronger. We can prove that they are stronger because of Gödel theorem. And they in fact prove more true pi1 sentences, assuming that these theories are true, that they describe the true sentences of arithmetic. But the question that is interesting for us is whether they prove more sentences relevant to computational complexity. This is what we would like to know. So this is one thing that we can ask. And another thing is, if we take some theories that differ in a way like P differs from NP and NP differs from sigma 2P and so on, then we can ask whether these theories form an increasing hierarchy. And this is open and probably very difficult problem, because here we cannot apply Gödel's theorem. Of course, we cannot prove that we cannot apply the theorem, but we know one thing, that the consistency of these theories is so strong that none of these theories prove the consistency of the weakest one. So we cannot use the consistency to separate these theories. Here's an example of what I am very much interested in. Given a problem and an algorithm that solves P, what is the weakest theory that proves the soundness of A? The soundness of A, I mean that the algorithm solves the problem. Or given a problem and a time bound T, you can ask what is the weakest theory such that for some algorithm T proves that A solves P in time T. Here's an example that appeared in our paper a long time ago. If factoring is hard, then the theory denoted by S12, which Sasha mentioned briefly, does not prove the soundness of any polynomial time algorithm for primality. So we are in the situation that we do know that there is a polynomial time algorithm for primality, but assuming a reasonable conjecture, S12 doesn't prove the soundness of this algorithm. So it's conceivable that that there are algorithms that are so complex or tricky or like use deep mathematics, that they are not provable in weak systems of arithmetic or set theory. So for instance, here we are not able to prove the soundness of AKS algorithm in any fragment of T2. But at the same time, we don't have a reason to believe that it is not provable in T2, except that we don't know how to do it. But there may be ways to argue that it's not possible by placing these things into a hierarchy of total function NP problems. But I am a bit digressing. So here's what I mean by soundness of an algorithm. So we have to be careful how we formalize these questions. We can always formalize an algorithm so that ZFC or any fixed theory does not prove the soundness. We can just embed the consistency statements of this theory into the algorithm, and then we are not able to prove that it is sound. But we can ask the opposite question, or something formally opposite. Is it possible to formalize every algorithm that its soundness is provable in Peano arithmetic or some other fixed theory? Now, this question is vague, and unfortunately, I'm not able to formalize it in a way so that it doesn't have a trivial answer. But this is what I would be very much interested. So instead, I will show today some related things that are not exactly this question, but of the same nature. What I'm going to present is something that can be presented as syntactic classes versus semantic classes. Syntactic classes do have complete problems, while semantic classes usually do not. We usually are not able to prove that there is no complete problem, but we can argue that there are some good reasons to believe that there are no complete problems. And what I'm going to talk about is three conjectures or several conjectures that are of the form that saying that there are no complete problems in certain classes. Russell in Pudlák doesn't like the word conjecture because he suggests to call things hypothesis, but in this case, it's something that I very much believe that they are true, that we should eventually be able to prove it, like we believe that P is not equal NP. So we don't say that P equal NP is a hypothesis.
Pavel, what is a semantic? Can you define semantic class?
Okay. So a semantic class is a class that is defined in such a way that we have to prove the defining condition that that the problem belongs to the class. So for instance, P is a syntactic class because we can present every polynomial algorithm in such a way that we know from the code that you write down that it runs in polynomial time. This is not the definition is not syntactic, but if you put into the code of the algorithm a clock that will stop the algorithm after polynomial number of steps, then we know for sure and that it will stop after polynomial time, and The dog makes noise here. I will have to do something. But other classes, typically randomized classes, are not of this form. You write down an algorithm and you accept this as a definition of a set in this class if you prove that it accepts the input with certain probability or not. Sorry, I have to make a short break to see what's going on.
The dog doesn't have a mute button?
No. Okay, so he's now quiet. Okay, so let's go on.
No, my question is, when we use semantic class, we're actually very loose about it, because I can always ask, when you say all the algorithms in some run in some time, I say, in what set theoretic universe are you talking about? So my claim is that when we use semantic classes, we are really very loose, and if we try to be precise, we will have to be better defined and to say in what class of models are we talking about.
Well, I don't understand this. So I think that the semantic class is defined precisely like RP, BPP. Of course, they may be equal to P, and then they are not semantic anymore because they can be defined syntactically, but otherwise they are semantic. So excuse me. Okay, sorry. So this dog is very clever. He can open the doors, so it's difficult to contain him somewhere. So anyway, this is not a precise definition, but we will see examples, and maybe it will be better to look at the examples that I will present. Is it okay, Moshe?
Yes, Sasha just gave a good answer. I'm happy with his answer.
Okay. Yes, maybe.
So just to say, Sasha said in the chat, semantic, there is no recursive enumeration of machines computing languages from this class.
Say it again.
Semantic, there is no recursive enumeration of machines computing languages from this class.
Yes, yes. The reason why we do have complete problems in syntactic classes is because we can enumerate the algorithms. Of course, it may not work always because the enumeration may be not so effective. But this is just a rule of thumb. It's not a precise statement. So let's get to examples. So the first item on my list or in the title is the set of tautologies. So let's restrict to DNF tautologies, but this is not important, just to be more concrete. We have proof systems, and a proof system is something that is complete, that there is a proof for every tautology, and sound that it doesn't prove non-tautologies. The completeness is easy to ensure by embedding some well-known proof system into it, and then say if we believe that the resolution is complete, then we can add to each proof system resolution, and then we know that it is complete. based on the assumption that resolution is complete, and we don't have to prove essentially anything. But the soundness is a problem. So if you have a very strong proof system, then you have to prove that it is sound. It's not, it may be a non-trivial thing. So this is how they are defined. And then we have polynomial simulations. I'll not define them because we know this very well, that you can, if you have one proof system and the other proof system simulates this proof system, it means that you can simulate the proofs of one system in the other. So there is polynomial time function that translates proof system from one into the other. And the conjecture is that this condition of soundness is indeed syntactic, that we cannot prove it easily, which means that there is no consistent theory that proves the soundness of all proof systems. So this may be one possible statement of this conjecture, and which is not maybe completely obvious, but easy, that this is equivalent to the condition that there is no proof system that simulates all other proof systems. I will call this optimal proof systems. An optimal proof system is that simulates all proof systems. And also I am omitting the specification polynomial. So simulates means polynomially simulates effectively, that you have polynomial time computable functions. I will not talk about the length of proofs.
Your red syntactic should be semantic, right? What did you say? Syntactic?
Also, yes, this should be semantic. Thank you. Yes. I have a kind of selective blindness. I cannot proofread my slides very well. And
your slides are semantic, not syntactic.
So, okay, and this conjecture is a fairly strong conjecture, because in particular it implies that exponential time is not equal to non-deterministic exponential time, and this is probably stronger than p is not equal to np. There is a related class, which is the class of disjoint NP sets. So this class consists of pairs of sets A, B, which are in NP, and they are disjoint. Again, we can define polynomial reductions between two elements of this class. This is quite natural. We can use either Turing reductions or many one, which means that if we have two pairs, then the first set should be mapped into the first set of the other, and the second should be mapped into the other. So this is something that you can easily imagine. And now the condition that these two sets are disjoint is a semantic condition. I have to be careful not to confuse the two things. Semantic because if you write down the definitions of these sets, you don't know whether they are disjoint unless you write down some trivial thing like all the sets in A start with bit 0, all the sets in B start with bit 1. So these are easily recognizable, but it's easily recognizable that they are disjoint, but in general, it may be hard to prove that they are disjoint. So we can state a conjecture that there is no complete disjoint NP pair. And this conjecture, again, is equivalent to this statement that there is no consistent theory that proves the disjointness of all disjoint NP pairs. Now, I'm stating this conjecture, at least the second part is stated a bit not quite precisely, because what does it mean that the theory doesn't prove that a pair is not disjoint? Whether the theory proves that the pair is disjoint definitely depends on how you formalize these pairs. So you need to write down a formula if you want to talk about its provability. So to state this precisely, one would need to say that it does not prove the disjointness of all NP pairs. However, you formalize the pair. So you take the best formalization for which it should be the easiest way to prove that they are disjoint. And for this, you are still not able to prove it in some theory. I mean, you're still not able to prove it in the theory. All right. So how these conjectures are connected? To show that they are connected, one can use the very important concept of canonical pairs of proof systems. If we have a proof system P, then the canonical pair of the proof system, as defined by Sasha, consists of a set of basically, you can view it as formulas that have short proofs, but to be more precise, what we use, we are using padding that limits the length of proof. So it's a pair of formula and a number represented in a unary, such that phi doesn't have phi has a refutation of length at most n. And the second set is basically sad, but we need something that looks similar to AP. So we also use padding, but it is just a padding that does nothing. So this pair somehow captures the strength of the proof system, because if P simulates Q, then the pair corresponding to Q is polynomially reducible to pair corresponding to P. This is very easy to prove, and the corollary of this is that the conjecture about disjoint NP pairs implies the conjecture about proof systems for propositional tautologies. Now let's get to total function NP. So TFNP means total function NP, which I define in the following way. A problem in total function NP is given by a binary relation that is computable in polynomial time and a polynomial bound, such that the relation defines multi-valued but total function. That is, for every a there exists b, which is at most polynomially longer than a, such that it satisfies the relation. So this polynomial bound is given just to be quite precise, but typically the polynomial bound is already implicit in the relation R. So I will often omit this polynomial bound and talk only about the relation. The problem associated with this relation, which has this property, is to find, for a given A, to find B such that it satisfies the relation. So now again, this condition is semantical. If you have a definition, if you have a formula for R or a polynomial time algorithm computing this binary relation, you never know for sure that this defines a total function. So you have to prove in some theory. Now, again, we have reductions between these problems. Now I will just use R and R prime for these problems. And these relations, this reduction are defined in the obvious way. We have either many-one relations or Turing relations, and it makes no difference for the conjecture that I'm going to state. So this many-one reduction is given by two polynomial time computable functions, f and g. So you want to compute a witness for A in a relation R, and you can do it in such a way that you first compute FA and find a witness for R prime, and from this witness B and A, you get the witness for A in relation R. But it may be more complicated to just using Oracle for the solution of R prime. Anyway, so we have a class and we have reductions, and then we can ask whether there is a complete problem. But let's just take an example so that we are sure that this concept is not empty, that there are probably total function NP that are not solvable in polynomial time. Because if everything is solvable in polynomial time, then everything will be reducible to everything. So then there will be a complete problem. So factoring is an easy example of a problem that is not solvable in polynomial time, but it's based on the assumption that it is hard. So the hardness of factoring simply means that this total function NP problem is not believed to be computable in polynomial time. So we have at least two different types of total function NP problems: those that are solvable in polynomial time, and those that are not. The conjecture about total function NP is much stronger than just saying that there are problems that are not solvable in polynomial time. The conjecture is that there is no complete total function NP problem. So this is far more stronger than saying that, that there is one problem that is not solvable in polynomial time. And again, this can be stated equivalently in logic, that there is no consistent theory that proves totality of all total function NP problems. These are, of course, hopeless conjectures because they imply P and Q and P. So do we have any reasons to believe that they are true? One reason why I believe this is true is that it's very much like computable functions in provably total computable functions in theories. If you have increasing theories with increasing strength, then you can show that also the class of provably total computable functions increases with the strength of the theories. It does not have to always increase, but at least in the examples that I showed at the beginning, this is the case. So the only difference here is that in total function NP, everything is polynomial, while here it is computable. So this formal similarity is one reason to believe that it may be true. The other reason is that we already have characterizations of probably total functions, probably total NP functions in fragments of bounded arithmetic. And these characterizations are of increasing complexity. We cannot show that they are of increasing complexity indeed, but at least formally they are of increasing complexity. Unfortunately, we are still not able to prove that at least in relativized world they are of increasing complexity. So this is one of the big open problems in proof complexity, to show that that this hierarchy of total function NP problems is increasing. This is something that is not hopeless. I believe that it only requires proving some very complicated switching lemmas, but so far nobody was able to do this. Like with the set of tautologies, we also have a similar connection, which are disjoint co-NP, pairs of disjoint co-NP sets. Again, polynomial reductions and Turing or many one are defined in the same way. And we can state the conjecture that there is no complete disjoint co-NP pair. Again, it's a syntactic class, so this is equivalent to, if true, then there is no fixed theory that proves disjointness of all co-NP pairs. And we have a similar connection as before, namely that the conjecture about disjoint co-NP pairs implies the conjectures about total function NP problems. So the situation so far is that we have two branches of conjectures. One is about tautologies and disjoint NP pairs, and another is about total function NP and disjoint co-NP pairs. But SAT is still missing, and you can now guess where SAT is. It's not obvious, so we will look at SAT. So I want to spend a bit more time with SAT because this is a program in SAT, at Simons, which is focused on SAT. So SAT is, of course, very much different from thought, but we also can consider proof system for SAT. And a proof system, what is a proof system for SAT? It's just any evidence that proves that a formula is satisfiable. What are polynomial simulations? They are exactly the same as for thought, that you transform proof in one proof system into another into a proof in another proof system in polynomial time. But the difference is that there is the standard proof system, one very special proof system, and this is just satisfying assignments. If you want to show that a formula is satisfiable, then the best you can do is to provide a satisfying assignment. And this proof system is polynomially bounded. While we believe that there is no polynomial bounded proofs for tautologies, we have trivially polynomially bounded proof system for SAT.
Well, I'm sorry for interrupting. If we're really running over time, but if it could take a couple more minutes.
Oh, sorry. I thought I was.
I'm sorry. We've been quite relaxed, but just realized. Sorry.
Okay, I don't have many slides, and I'll skip something, so I will finish. 5 minutes, or is okay, or?
Oh yeah. Sorry for that. I just looked at the clock. Oh.
Yes. So. Okay, so so the situation is different, but still there may be proof systems that are not polynomially bounded. Now, an example of a proof system for SAT that is probably not polynomially simulable by the standard proof system is the following one. You take the standard proof system and you add basically factoring into it, which means that you take as a proof any satisfying assignment, or if the formula expresses that n is not a prime, then n will be just the proof of this. And it is not difficult to see that if factoring is hard, then the standard proof system does not polynomially simulate the system, because if it did, then we would get a satisfying assignment for formula phi, and this is what we believe is not possible. All right, so let me quickly go over this natural proof system for SAT. You can get natural proof system for SAT if you realize that phi is in SAT if the existentially quantified formula as a quantified tautology is a quantified tautology. And then you can use proof system for quantified tautologies. And you have to go faster. What is interesting is that the standard proof system polynomially simulates the G star 1. I'm not going into the details about it. And the point is that is the witnessing theorem of Cook. So the bottom line is that if you have a witnessing theorem in a proof system, then it essentially means that the standard proof system polynomially simulates it. Okay. If there is an optimal proof system for SAT, then there exists a complete problem in total function NP. I wanted to prove this, but I don't have time, so it's a pity because it's a simple proof. So let me finish by saying that we can state a conjecture that SAT doesn't have an optimal proof system, and and the proof that we skipped gives us that total function NP conjecture implies the SAT conjecture. So we can place SAT into the diagram, and it is between P unequal NP and total function NP conjecture. Now, and these things have been read about. So we know that many things are different. In particular, these two branches are really distinct branches. But unlike showing these implications, which are usually easy and more or less straightforward, relativizations are pretty technical and complicated. So we still don't know whether these two are different and these two are different. Okay, thank you.
Thank you so much, Pavel. This is really, really interesting. Okay, we are running a bit over time, but maybe
Moshe has a question.
Okay.
Just a quick question.
Yep.
So Harvey Friedman has this program showing that these stronger set theories end up proving kind of you need strong set theory to prove very mathematically looking statement about kind of numbers, just statement about number theory and things like that. And I wonder whether you can use his program to show that these stronger set theory, like axiom, strong cardinal axioms, prove things that actually they have computational meaning.
I wish I could, but I cannot. Yeah, so the problem is that essentially what we are able to do is just somehow to rephrase the consistency in some combinatorial way, but it's not anything that can be interpreted as a statement about computational complexity. But this is well, I would like to do it, and I'm thinking about it, but I don't know how to do it.
Thank you.
Thank you so much. And maybe while Shai is setting up, if anybody has any more questions for Pavel, and thank you so much, Pavel. This is fantastic. This is really interesting.
Antonina, may I ask a question? Pavel, thank you for the talk, first of all. My question is the following. Consider the conjecture that that NP intersect co-NP, which is a semantic class, has no complete problem. Where would this conjecture fit in your diagram of connections between the conjectures?
This doesn't fit into any of the branches, so it's in the middle. It's stronger than, of course, P unequal and P, but it's in the middle. So we are. I'm not sure that we can show by relativization that it is not in any of the branches. Maybe Erfan Haniki, if he's connected, can tell you more. But it seems that this is in between.
Thank you.
Thank you so much.
It's possible that there is a third branch which is based on this, but I don't know other than this problem in this direction. So sorry for being a bit longer than I expected. Oh,
I'm sorry for kind of making it more loose than needs to be. Thank you so much, Pavel. This has been beautiful. So let's, if you don't mind, let's postpone question till later and till after the talk and to gather town and start our grand finale of today's, which is the talk by Shai Ben David about, as you could see, if P versus P can be independent of the axioms of reasoning. And so just a couple of words to introduce Shai Ben David. His work spans a really vast range from kind of from set theory of set, kind of really deep set theory to really practical machine learning with algorithm and complexity and logic and all sorts of things in between. And Shai can connect all those disparate things and show the relations where, you know, it's hard to imagine that there could even be relations. For example, independent result of a machine learning problem. This is one of your NeurIPS best paper awards, right?
No, not this
one. That one? Not this one? Okay, so you have other papers which got NeurIPS best paper awards and such. Anyway, so Shai's work spans huge area and it's really beautiful. And today he's going to tell us about that really cool result about SAT and P versus P and independence, please.
Okay, yeah, so I'll try to be not technical. I know we're running behind time. So yeah, so I want to look at this question of whether P versus NP can be independent of set theory. And here, I mean, as in contrast to what Sasha was saying, when you look at negative results, the stronger the system you can show that cannot prove something, the more the stronger the result is. So I'm really interested in much stronger systems. So I'm not going to talk about SAT or anything, how to solve SAT, but so what was the talk about? So when you're faced with some hard mathematical problem, there's always the temptation to think that maybe this problem is inherently irresolvable. Maybe the reason that we fail to find answers is not our lack of wisdom, but rather that no answer, no proof exists. I mean, that's following Gödel, we know that this is always a possibility when we're facing an open problem. So the goal of this research was to see, try to ask, why do we fail to resolve some basic computational complexity questions? Could it be that P versus NP or other computational open problems are unresolvable in set theory, which means we have no tools of proving that the answer. And more concretely, is it likely that that the tools that we have in mathematics are inherently too weak to determine relationship between complexity classes? So, I mean, if we believe in such a direction, then we should direct our efforts to answering these logic-oriented questions rather than struggle with directly computational complexity issues, because maybe it's hopeless. Maybe by showing that, I mean, and that's, you know, the kind of the line of research that Sasha was taking and others in this community that don't try this direction because it's futile. So what do we know about independence proof? Just to remind everybody of independence proof of set theory. So Hilbert's program was the hope to develop a formal method that will resolve all mathematical questions. And of course, Gödel's incompleteness result showed that this plan is bound to fail. Every reasonable mathematical framework has irresolvable question, and we will call a problem independent of a theory T if T cannot prove neither the statement S nor its negation. And Gödel showed that the consistency of a theory T is always such an independent statement with respect to T. But of course, what we are interested in is, are there relevant real mathematical questions that fall in this category of being unresolvable by set theory, which means unresolvable by what we call mathematical proof. Okay, so what do we know about that? So what is the set theory that we look at? So a formal theory that defines, kind of commonly define what mathematical proof is about is the set theory ZFC. There is a slightly weaker theory which talks about arithmetic, pan-arithmetic, we all know it. And just to mention that pan-arithmetic is equivalent to set theory if we just delete the statement there exists an infinite set. So, and since ZFC can prove the consistency of pan-arithmetic, we can build in ZFC a model for number theory. Then we know that it's strictly stronger than PA, even with respect to statements about natural numbers, because the statement pan-arithmetic is consistent can be phrased as a statement about natural numbers. So here is a statement about natural numbers that you can prove with ZFC, with the assumption, with the extra axiom there exists an infinite set. And you cannot prove this statement in pan-arithmetic, although it is a finitary statement about natural numbers. Okay, so that's kind of the background. And Paul Cohen showed that there are really questions that are independent of set theory. The continuum hypothesis and is a kind of a sounding example of this. And since then, there have been many independence results in set theory. It started with cardinal arithmetic and infinite combinatorics, group theory, topology, functional analysis, algebra. And recently we had, as Antonina mentioned, we had an independence results of set theory for very, very basic question in machine learning. So what can we say about independence results for computational complexity? Do all of this kind of machinery of being able to show that things are independent of a strong theory does it apply to computational complexity statements? So there is an old result of Hoploff and Hartmanis that says that for any theory T, we can find a Turing machine such as the oracle complexity with respect to this Turing machine cannot be decided in T. This is kind of a diagonalization trick and talks about the oracle P versus NP with respect to some specially crafted oracle. So that was kind of the first result. And then there were several results of independence of weaker fragments of arithmetic. We already mentioned here some. There's some. First, there were artificial fragments that were kind of meant to be weak enough so that you will not be able to prove much with those weak fragments. Then there was bounded arithmetic independence, like the famous independence results of Sasha, and all kind of limiting the proof techniques. So relativized the proofs, that was the oracle result of Baker, Gill, and Solovey, and then Razborov and Rudich showed that if you limit the proofs in another way, it's exactly what Sasha was talking about, then there are statements you will not be able to prove. And then later there's the algebraic proofs of Aronson and Wingersohn. But can we prove the independence of P versus NP from set theory? Could this be the case? So there are inherent limitations. The point is that to realize that since Paul Cohen in 1960, Paul Cohen introduced the technique of forcing, and in some sense, we do not have any new techniques for showing independence of set theory. In a high level, they all follow the same pattern. I will not get into describing this pattern, but important to notice about it, that all the proof techniques that we have for showing independence from set theory, they cannot show independence of any statements that involves only natural numbers, only finite sets. So we do not have any technique that has a hope of showing independence of statement like P versus NP, because those are finitary statements. There exists a Turing machine such that, and there exists a case such that for all formulas and so on, everything is finitary. All the tools that we have for showing independence from full set theory can be shown not to be able to show such independence. So we have to go to, so that's what I'm trying to explain why it's a finitary statement. It's for every code P, there is a Turing machine and a K, and so on. We know that P versus NP can be written as a finitary statement in the language of number theory. So what can we hope to prove? So I'm saying we don't have any tools that will be able to show independence of P versus NP of full set theory, but what about non-provability from Peano arithmetic? That's kind of the next best thing that we could hope for. So this is a weaker theory, and a weaker theory, it would be easier to show statements that it fails to prove naturally. And it will be a very interesting result because independence with respect to Peano arithmetic would be quite satisfactory. It will tell you that without using a statement, there exist infinite sets, we will not be able to resolve our complexity questions. So showing independence of Peano arithmetic, I think, will be a kind of, could be something to hope for as a mathematician, because it really tells you that we cannot resolve P versus NP. I mean, the possibility that for having to resolve it, we have to assume the existence of infinite sets or even stronger infinite cardinals does not, we have no way of incorporating or even imagining how it could be relevant. So this could be an interesting goal. So I can go back to my first slide. What I'm saying is, rather than trying to solve P versus NP, maybe what we should do is try to show that it is independent of Peano arithmetic. if it's independent and parallel arithmetic, in some sense, our efforts to show it, to prove it, are bound to fail. Okay, so do we know of any independence from parallel arithmetic of real mathematical statements? So as I mentioned before, we do have results about independence from ZFC, and of course, there are independence from parallel arithmetic, but these are all about statements which involve infinite sets. So do we have any statements about independence from parallel arithmetic of real mathematical statements? Of course, the consistency of parallel arithmetic is independent of parallel arithmetic, but we want to talk about inherently mathematical statements. So the first such result was Paris and Harrington, and that was a very big breakthrough at the time. They took a natural version of Ramsey theorem that we can prove in ZFC that this is a true theorem. It's just the usual Ramsey theorem, but just, I mean, I will not repeat it, but just mention to those that are familiar with Ramsey that the only addition here is that the homogeneous set, that the existence of this set is guaranteed by Ramsey theorem, should be larger than the first natural number in this set, which seems like a small minor addition to Ramsey's theorem, and it's really indeed provable that it's true, but they showed you cannot prove it in parallel arithmetic. So that was kind of giving hope that there are mathematical statements about finite sets that are independent of parallel arithmetic, although they're provable in ZFC. The question we are aiming for is to ask, is it likely to be the case for P versus NP or other computational complexity problems? So there are similar results later, statements about natural numbers. It's fun to read these things, the Hercules and the Hydra. I don't know if you heard about this. It's kind of a puzzle that you have a tree and you have leaves from the tree, which are heads of the Hydra, and you are Hercules and you have a sword and you are cutting heads, but each time you're cutting heads, it grows more heads, and it grows more heads in a scary way, the formula. And still one can prove that no matter how bad as Hercules you are, you will eventually kill the Hydra, but this eventually is very long. And to prove such a system, so to prove such a statement, we can do it in ZFC, but we cannot do it in parallel arithmetic. And again, it's a finitary statement. You're playing a game against a finite tree, which is the Hydra. The interesting relevance to us is that the structure of P not equal in P is syntactically, it looks the same as the Paris-Harrington, because the Paris-Harrington is a Ramsey theorem. It says for every arity and size and the number of colors, there exists a homogeneous set of such size. And here, the P not equal in P have a very natural, a very similar syntactic structure. It says for every x, there exists a y such that phi xy, which is like the Ramsey. For every parameters, you have and size, you have a homogeneous set. And the statement, this set is homogeneous and of this side, does not contain any unbounded quantifiers. And it's the same with P versus NP. Just you want to show that for every program and every bound or the polynomial of the runtime of the program, there exists an instance of such that this program will give you the wrong answer. So the statement is syntactically looks like the Paris-Harrington. So we could hope that maybe we could show a similar result independent of parallel arithmetic for P not equal NP. Okay, so that's what I was set to try to understand. And the conclusion of this work, if we jump right to the end, is that if on one hand, if SAT can be solved in almost polynomial time, so say P is not equal in P, but SAT can be solved in time which is very, very close to being polynomial, and I'll elaborate on it later. If SAT can be solved in almost polynomial time, then you cannot prove that P is not equal NP. And now the concrete notion of almost polynomial depends on the theory in which you want to prove it. So for every theory, there is a notion of close to polynomial, such that if SAT can be solved in such close to polynomial time, then that theory will not be able to prove the separation between P and NP, because the SAT has a solution that looks almost like polynomial, and the theory, the almost will be so fine that the theory will not be able to distinguish between the two. So that's not so much of a surprising result, but it's something that's worthwhile to bear in mind, and I'll get back to it a bit later. But the surprise here is that we also can show the other direction. So if the theory is sufficiently strong, then the reverse statement also holds. Namely, the only possible reason for failure of the theory to prove that P is not equal to P is that SAT can be solved by an algorithm which is almost polynomial time. So in some sense, it says, loosely stated, that if you can prove that a strong mathematical theory cannot show that P is not equal in P, you will imply that SAT has a solution which is almost polynomial time. So solving the logical statement, the higher level logical statement, P versus NP is independent of set theory, will be as hard as coming up with a polynomial, almost polynomial time for SAT. So in some sense, that's the main conclusion of this talk, that there's no point you don't get much advantage by struggling with logic and trying to show that P versus NP is independent of set theory, because this will be as hard as showing that you have a polynomial algorithm, or almost polynomial algorithm for SAT. Okay, so that's, at this point, I said the most important things of the talk, and now I want to go a little bit into the technical details and kind of convey the intuition, which is not so complex at all, of why this is indeed the case. So we would consider, what do we mean by almost polynomial? I'm talking now about SAT has a solution which is almost polynomial time. So what do we mean by almost polynomial? So we look at running time, which is n to the fn, where the exponent fn grows very, very slowly. So it means that the running time has a constant exponent for huge stretches of input length. So the function fn, I want it to grow very, very slowly, the exponent of n, of the runtime. And if the function grows very, very slowly, we can view it as the inverse of a fast-growing function. So it will be, in some sense, it's easier to talk about how fast a function grows rather than talking about how slow it does. So we'll talk about the inverse of the function, which is the exponent of the runtime. So here are some fast-growing functions, the Wiener hierarchy. So this is a way of constructing very fast-growing functions. So f1 of n is 2n. And now for every countable ordinal lambda, f lambda plus 1 of n is just you apply f of f, you compose n time f lambda and apply it to n. And if you take a limit ordinal, then you also have to define it for a limit ordinal. And for a limit ordinal, you just, at the n step, you take a sequence, delta n, that converges to delta, to your limit ordinal, and that to compute f of n, you apply the function composed delta of n times. So this is a way of defining a very fast growing functions. The Ackermann function is just f omega is the first infinite ordinal in this sequence. Is already the Ackermann function, but then as we see here, we can keep going. We can applying it further and further and further and get faster and faster growing functions. That's the kind of the functions that we will talk about, whose inverses will be the exponents of the runtime, if indeed you could prove independence of P versus NP. So just to demonstrate here, I mean, this is a sophisticated audience, I don't have to convince you, but like F2 of 3 is already a crazy number. Somehow something hides it for me, but yeah. Anyway, anybody can do these calculations. It's crazy fast going. Even F3, F omega is Ackermann's function, and we go beyond that. Okay, now how far beyond that we go when we want our functions to grow very, very, very fast? So it's common to denote by epsilon 0 the first ordinal such that omega to the power alpha equals alpha. The powers here are ordinal powers, but, and I will not get into the definition, but this is the limit of omega, omega to the power omega, omega to the power omega to the omega, and we take the countable limit of this. So this is epsilon 0, and we will be interested in the function f epsilon 0. So we take this Wiener hierarchy and we push it and push it and push it. We go through Ackermann function is just here at f omega, and then we keep going and going and going and going, and we get to this stationary point, fixed point of this function, and we take this crazily growing function. Why do we care about this function? So we care about such a function because it has, I mean, the next step is the way I connect fast-growing functions and complexity conjectures. I mean, this is fun to talk about fast-growing functions and Hydra and so on, but it does relate to computational complexity. So how do we make the connection? So given a complexity class which you can enumerate as a countable set of algorithms, as some canonical enumeration of the class. I guess this is what Pavel was calling a syntactic class. And given a language, I can define a function. And the function, it measures how well can this class approximate the language L. So this function at the point I, it is the maximum over, so I go over M1, M2, M3, and so on up to Mi, and I see which of them can compute L correctly on longer initial segments. So again, I go over all functions. Here is my class, M1 and 2 and so on. I'm going over at point I, I'm going over all the first I machines, or first I programs. And then for each of them, I look at the minimum point where it fails to compute my language L. And I take the maximum. So this tells me how many machines do I have to consider in order to correctly compute the language L on the first how far can any of the first machines can compute my language? This is what we are doing here. So we define a function that measures how well can a class of functions approximate a given language. And it is easy to realize that this function is total if and only if L is not in the class. Because if L is in the class, there will be some I such that there will never be a failure. This machine, Mi, will compute the class correctly. And we are just looking at the first time that all the first I machines fail. So this is a total function. For every I, there is a number R of I, if and only if the function is not in the class. And furthermore, the faster this function grows, the closer is L to the class. Because it means that fewer machines, right? F of I tells me how far could any of the first I machines compute L correctly. So if it grows fast, it means that I need few machines to compute big stretches, L on big stretches of x's. So the faster this function grows, the closer is the class, the function, the language L to the class C. So here we kind of measure how far, it's not just P not equal and P, but I'm trying to measure how far is SAT from the class of polynomial time functions. So it gives a quantitative measure. And this is the function that will apply our knowledge about our discussion of fast-growing functions. So if we enumerate all p-time machines, and we assume that we have some kind of easy mapping, computable mapping from index I to the code of the ith machine, and we can, without loss of generality, assume that the ith machine is bounded by n to the log I. I mean, we're just enumerating polynomial time machines. And then we can get this nice connection between this function R and the computational complexity of computing SAT. So if R is this approximation function of SAT by P, then SAT is in deterministic time d to the log g of n for every function g that bounds R minus 1. So now let's stop and see what it means. R is how far I can approximate SAT. R is a function that if SAT, that grows very fast. So R minus 1 is a very slow growing function. And so G is just a computable function that upper bounds R minus 1. And it means that if SAT can be approximated well by this procedure, by enumerating all polynomial time machines, then SAT is in deterministic time, which this is a very close to constant, very slow growing function, because R is fast growing, R minus 1 is very slow growing. I take the log of it, and so I have this in the exponent. The exponent is almost a constant. So we're using fast growing functions, we're looking at the inverses as a way of measuring how close SAT is to P. And the corollary is that the approximation rate of P by SAT gives us a notion of almost polynomial time algorithm for SAT. So if the approximation rate is a fast growing function, then SAT is really almost polynomial. The exponent is almost a constant. Okay, so at this point, we have the ingredients for our reasoning. We have the notion of fast-growing function and the relation to SAT and the class P. But of course, what we want to do is relate it to probability. So what's the connection between this and probability, or in particular to the probability of P versus NP? So a function is called probably recursive. I guess you all know it. If you can prove in your theory that it holds, that I have an algorithm that computes this function and holds on every input, and probably recursive functions with respect to PA and PA1. I haven't yet defined PA1, I'll define it in a second. It's the pi1 closure of PA. It's the same, so we can talk about being provably recursive without making this distinction. And there is the Wiener theorem. And the Wiener was is from this hierarchy. And the function is every f alpha for alpha less than epsilon 0 is provably recursive. And this is if, in some sense, it's if and only if. If a function is provably recursive, then it is dominated by some f alpha. So this Wiener hierarchy, what it gives us is a way to determine how fast can a function grow and still be provably recursive. Still, we could prove that for every x, there is f of x. And the answer is that roughly the bound is this f epsilon 0 in the Wiener hierarchy. So the corollary is that if a function grows very fast, it's not dominated by any of those functions, then Peano arithmetic and its closure pi1 functions, by pi1 statements, cannot prove that the function is total. I guess I don't have time to explain the result. It's a classical result. It's a beautiful result, but if a function grows too fast, you cannot prove that this function is total. And the Paris-Harrington, actually, the proof that Peano arithmetic cannot resolve this Ramsey type theorem is exactly by showing that the Ramsey number, that you take parameters and you want to ask how fast should your graph be in order to get such a homogeneous set, is such a fast growing function that it's beyond the scope of what Peano arithmetic can prove it is complete. And in Peano arithmetic cannot prove that it's complete. It cannot prove that for every input parameters, there is indeed a large enough graph that will give you a homogeneous set for these parameters. So this is exactly the tool, the machinery behind the Paris-Harrington independence result. And most of the proofs of independence from Peano arithmetics of statements that we can prove in ZFC, in set theory, have this kind of nature. They generate a very fast-growing function and show that this fast-growing function is beyond the limit that is stated by Wiener's theorem. So this repeats in other independence proof with respect to Peano arithmetic. So what we can conclude here, that if the approximation rate of SAT by P is very fast-growing function, then Peano arithmetic cannot prove that P is not equal in P. And so if SAT can be solved by an almost polynomial time algorithm, then Peano arithmetic will not be able to prove that they are different. Okay, so that's one direction of our theorem. Maybe the more interesting direction is the other direction. So the inverses of fast-growing functions are functions that are very, very almost constant. They're on big stretches. They're constant. I'm trying to rush because I see the clock. We're getting too close to 2 o'clock here and to the end of the recording. So what I'm saying is that if a function goes very fast, if this function R, the approximation, goes very fast, then there are long stretches on which SAT can be solved in a fixed polynomial. So the next step is showing that this is the only reason for non-probability of P versus NP. And I show it with respect to the theory PA1. PA1 is I add to Peano arithmetic all the pi1 true statements. Now PA1, so it's Peano arithmetic plus all the pi1 formulas that are true in standard models of arithmetic. And what do we know about this property of PA1? It's not a recursive theory. That's a big negative, but there is some notion of some sense of representation independence. I mean, it has exactly the theory that we need in order to be able to show that if you have two Turing machines, to prove that two Turing machines that compute the same function are indeed computing the same function. So in order to show representation independence of Turing machines, we need the theory PA1. And so it's, in some sense, it's a natural theory to consider when we want to talk about independence of runtime on Turing machines. And we can also, nice properties, if P equals NP, then PA1 can prove it because you can have this polynomial time algorithm, and PA1 can prove the statement for every input it computes SAT correctly. Okay, so we switch to the theory PA1, which is much stronger, and now we have the theorem that PA1 proves P equals not equal to P if and only if the approximation rate of P is low. Oh, in other words, so I mean, before I talk about the proof idea, what we care about here is to show that PA1 will be able to, if SAT is far from P, PA1 will be able to show it. And the only reason that it cannot show it could be that SAT is very, very close to P. And the proof idea, I guess we don't have much time for proofs now, but we can write this as a pi1 statement. So the conclusion is that if PA1 fails to prove P not equal P, then SAT has almost polynomial time algorithms. And more on the significance, so I want to show that if PA1 cannot prove that they are different, I mean, then in some sense we cannot distinguish in independence proof between PA1 and PA, because the generic way in which we show that the theory does not prove some statement, the Paul-Cohen forcing style, is to start with a model. We assume that the theory is consistent, so we have a model M. We construct a submodel in which you get the opposite of the statement, and such a submodel will also satisfy the pi1 theory of the first model. So what I'm saying, any tool that we have with the hope of showing that something is independent of Peano arithmetic will also show us independence of PA1, and therefore, if we could show independence of SAT, of P versus NP, it will mean that SAT is very close to P. So this is the bottom line. So if it is provable that P versus NP is independent of PA, then SAT can be solved in deterministic time t to the g or n, where g is a very, very slow growing function, or g minus 1 is a very fast growing function, which will mean that SAT is almost in P, and that's if and only if statement. I think I've just, we have similar results for silicon complexity. We can show that, for example, if Peano arithmetic cannot show if P versus NP is independent of Peano arithmetic, then there are no one-way functions. And all kind of results in this nature, but I'm out of time, so I will stop here and take some questions, if we can still take questions.
Thank you so much. Yeah, please ask questions, and sorry for running over time, but please do ask questions. If nobody asks, may I ask a really naive question?
I have a question.
Oh, yeah, you have a question? Okay, yes. Go ahead.
Okay, does the proof technique also allow you to go further down in the strength of the theory, for instance, to replace Peano arithmetic by I sigma 1 and F epsilon naught by Ackermann?
That's an interesting direction. It seems that, I mean, it's an interesting direction. I haven't thought about it. I haven't thought about Wakel theories. I mean, as Sasha was saying right at the start, I come from working on ZFC, but yeah, I think it's a very interesting question. It's not inconceivable.
Okay.
More questions? Well, oh yeah, please, Pavel. Yeah.
Yeah, the comment. So I understand the message is that the problem is that we are not able to distinguish between PA and PA1. We are not really able to understand what are the basic things in Peano arithmetic. We know what is the induction, but if Peano arithmetic was formalized with some stronger basic theory, then everything that we are able to prove about Peano arithmetic would be the same. And this is what I completely agree with you. But I would like to add that the similar thing is in complexity theory, that we are not able to distinguish computations that have different basic operations, like say if we allow Turing machine an access to Oracle and say, well, what the Oracle computes is the elementary operation, So then various things can happen, and this is the relativizations. So that
I think it's an interesting
explains-
analogy.
Sorry.
I think it's a very interesting analogy, right?
Yes. Okay. Thanks.
Actually, a question to both of you, because I kept thinking about the relation between your talk, Shai, and Pavel's talk. Pavel talked about semantic classes and the question of complete problems, and you heavily use the fact that P is a syntactic class.
Right.
Is that right? So is there any kind of connection between those?
Yeah, I really don't know. I mean, I use very heavily. I mean, all of this line of all of this machinery is about syntactic classes, right?
And Thomas is asking you to show the second last slide again.
Okay. This one or the before that?
You can unmute and share.
Before that. Yes. Thanks.
Right. Yeah. This is about why we cannot distinguish PA1 from PA that Pavel was talking about. Yeah. So do you want me to repeat it, or you want to ask something about it?
No, thank you.
Oh, okay.
Yeah. So, Shai, I have very naive question. So assume that I am telling you that NP is not a subset of quasi-polynomial time in the real world, right? It means, or maybe I missed something, you are saying that it implies that P is not equal to NP slightly weaker statement is provable in piano arithmetic.
Right.
Is
Yeah.
it what you are saying?
Yeah. Yeah,
Okay.
this is a rough way of putting it, right?
Sounds very strong to me.
Yeah.
No, it's not provable in piano arithmetic. It's provable in PA1.
And that
No,
it's proven.
I'm sorry. Move it one slide further, or where you have a result here. It says PA.
Yeah, but here it is here I have the caveat by any method known today. So what Pavel was saying correctly, I mean, provably we can show it will be provable in PA1, but there is no mathematical tool that will distinguish PA1 from PA. So now we have to take a second step on top of it and saying by existing tools.
Okay, good. Okay, thank you.
More questions, comments to any speakers? To and from any speakers? Okay, thank you very, very much, everybody. This was such a fantastic session. Sorry for running over time, but I don't want it to end. This is fantastic. So if people are interested, they could go to, if you are an attendee, I posted a link to GatherTown in the chat. This is a workshop GatherTown. And if you want to, anybody who wants is welcome to come there and we could chat. And yeah, so thank you so much, Sasha, Pavel, and Shai. All three of your talks are so inspiring and really make you think about, you know, about the basic questions. So thank you very, very much.
Thank you.